Welcome back. We continue with week 6 logic coverage criteria. Just in the last week, we saw a second example of how to apply logic coverage criteria to test predicates that come in source code within a method or a procedure. We'll now deviate slightly and look at logic coverage criteria as applied to predicates that come in other software artifacts. What could be other software artifacts? There could be requirements documents, there could be design documents. Logical predicates do come in all of them. In this lecture, we will look at requirements, which is specification, and look at logic coverage criteria for predicates that occur as a part of specifications and see how we could test by using the coverage criteria that we've learned till now. Just a recap of specification. As I told you, specifications are basically requirements about a software artifact. They can be written in a formal language which has mathematical meaning in a modeling language, or they could just be written in English. Typically, specifications have several conditions which are a rich source of logical predicates, and we could use logical coverage criteria to test them. If they are given in English, it's obviously the tester's job to derive these logical predicates from the specification and apply the criteria to them. Where do they come? They typically are written as preconditions. You remember we saw the Q example when we looked at graphs, and we said whenever you use Q as a data structure, you have several constraints on what the properties of the queue is all about. You can't dequeue if the queue is already empty. At any point in time, the number of NQ calls should be greater than or equal to the number of DQ calls, and so on. So whenever you use a particular software artifact or even as a requirement, you write a lot of conditions on that. There could be preconditions, postconditions, assertions, some properties that are invariant like we saw in that of a queue, which all can be expressed also as logical predicates. For Q, it was natural to express it as a graph or as a finite state machine. For certain other things, it could be natural to express the same kind of sequencing constraints as logical predicates. So we'll see one example where a sequencing constraint is most naturally expressed as a logical predicate, and use the logical coverage criteria that we saw to check for requirements in that code. So how do preconditions in programs come? Programmers, while writing preconditions, often include the preconditions in their methods. They are typically expressed as comments in the method headers, for which there will be code written somewhere to test for it. Like for example, suppose you say I take a piece of software that accepts a name, accepts address, which includes the name of a state and pin code. You'll obviously have some constraints which says that name cannot be an empty string. It cannot have special characters. State must be a valid state. So a simple way of enforcing would be to give a drop down list of state names. Pin code must have 6 digits and so on. So in logic, a comment like this that you see here, name should not be empty. State must be valid. Pin code must be 6 digit. I could express it as a predicate which says name not equal to empty string, and state is a member in a list of states that I am populating. Pin code is a 6-digit number. So it's at least, it's a number between the 6 zeros and a number between this 999 counted in terms of digits, not absolute value of a number. Several such preconditions could occur as simple combinations of clauses. Here if you see, there are 3 clauses. First clause here combined with an AND, second clause combined with an AND, third clause. So it's useful to study these special simple combinations of clauses, because to test for active clause coverage, if it's a simple combination of clauses, it's easy to test for active clause coverage. So 2 such simple combinations exists. We call them as normal forms. One is called a conjunctive normal form and the other one is called a disjunctive normal form. What is a conjunctive normal form? So the word conjunct means and. The word disjunct represents the logical operator or. So in conjunctive normal form, the outermost connective that you find is a conjunct, or the logical operator that you find at the outermost level is an AND operator. So we say a particular predicate is in conjunctive normal form, abbreviated as CNF, if it consists of clauses where each clause is a disjunct or as a standalone clause, and the clauses are connected by the AND operator. So these are examples of how a conjunctive normal form looks like. In the first case, it's a direct AND of some number of clauses. In this example, we have 3 clauses. So A and B and C. It's an AND of 3 clauses. Here, it actually has 4 clauses, but there are brackets. So it says A or B is the first disjunct or the first part which is connected by an OR. C or D is the second part which is connected by an OR, and these two are connected by an AND. So the outermost connective is an and these ANDs are connected by ORs. Is that clear? So this is what we mean by conjunctive normal form. So the third one says the outermost connective, please note, is an AND. Inside that there are 2 parts. The first part has 3 clauses connected only with an OR operator. Second part has 2 clauses connected with an OR operator. So in general, if you find formulas of this structure where the outermost connective is an and inside the parts, which are also called disjuncts, we have only ORs, and individual entities can be either standalone as you see here or not of that particular clause. Then we say that the predicate is in conjunctive normal form. If a predicate just has clauses, not disjuncts, like the first one that you see here, A and B and C, then it's very easy to do active clause coverage. All that you have to do is a particular major clause can be made active by making all the other clauses true. Is that clear? Because it's just a simple AND of the clauses. So active clause coverage is a test requirement for predicates which look like this, like a simple conjunct of clauses, is basically all true values followed by false somewhat along the diagonal of the table. I hope you understand what I mean by the diagonal of the table. Like for example, in this case, we have A and B and C. The way it looks like is you have all 3 true, A true and false, which is this second row. Then in the third row B is false, in the fourth row C is false, and false just proceeds along the diagonal like this, comes down on the left from the right to the left, and the test requirement is just this. On the other extreme, you have disjunctive normal form, which is basically the outermost connective here is an OR, and you have ANDs inside them. In conjunctive normal form, the outermost connective is an and you have ORs inside them. In disjunctive normal form, it's the exact reverse. The outermost connective is an OR and you have only ANDs, no other logical operators inside. So a predicate is supposed to be in disjunctive normal form, abbreviated as DNF, if it consists of clauses, also called as conjuncts, like in this case, second case and third case, that are connected by a disjunction operator. So first, all 3 clauses A or B or C connected by an OR, A, B, C are connected by an OR. The second case, 2 disjuncts A and B, C and D are connected by an OR in the outermost connective. In the third case, again the outermost connective is an OR. Inside you have A1 and A2 as the first conjunct, and B1 and B2 and B3 as the second conjunct. So in disjunctive normal form, the outermost connective is an OR. Inside, either you just have clauses or you have disjuncts of clauses. To repeat, in conjunctive normal form, the outermost connective is an and either you have clauses or you have disjuncts of clauses. So just as we saw, if I just have clauses connected by an OR, like here A or B or C, the major clause can be made active for ACC criteria by making all the other clauses false. That's because of the presence of OR. So the test requirement for ACC is all false, followed by a diagonal of true values. Is that clear? So this is the table that depicts it. The first row is all false, second row is true, false, false, third row is false, true, false, fourth row is false, false, true, and so on. So several of the logical predicate conditions that you find as preconditions like this as a part of specifications either come in conjunctive normal form or in disjunctive normal form as simple conjuncts or as simple disjuncts. So you could use ACC criteria to come up with test requirements very fast. We will see an example of such a thing. Let's say you have a program that that takes 2 dates within a span of a calendar year and calculates the number of days between these 2 dates. So you could say take 2nd February and 20th May and give me the number of days between 2nd February and 20th May of a particular calendar year. So this is that program. It has this method called cal, which takes first month, the February, second, first day, second month, in our example it was May, 20th, second day, and which calendar year. So from day 1 to in month 1 to day 2 in month 2 for a particular year, calculate the number of days in between. Obviously, this kind of method that does this calculation should have some preconditions. What would be the obvious preconditions? The day and the month must be in the same calendar year. That's not an important thing, but that's what this method is supposed to do. So we might as well put that as a precondition. Day and month must be in the same calendar year. The first month that you specify should come before the second month. First day that you specify should be a valid day, should be between 1 and 31. Both the months should be valid months between 1 and 12. And year you assume is within a certain range because the number of days will be heavily influenced by whether the year is a leap year or not. Other months have the same thing, only February will change. So these are all preconditions. If you see, they can all naturally be specified as a logical formula. So the rest of the slides here, couple of slides, contain the actual code of the program that calculates the number of days between a particular date in a month to another date in another month in the same year. So that's called, it first declares a local variable called num days. It says if month 2 is the same as month 1, that is you want 2 days, you get 2 days within the same month, you just have to calculate the number of days. Then you say number of days is nothing but day 2 minus day 1, subtract 1 from the other. Otherwise, you first set up. This is basic thing that sets up the number of days in each month. First one is 0, January has 31 days. February I keep it as 0, I'll populate it as 28 or 29 based on whether it's a leap year or not. March has 31 days, April has 30 days, May has 31 days and so on all the way till December, till the end of the array. That's days in a month. Now for the February, which is the third entry here, the second month, we calculate whether it's a leap year or not. The formula for leap year is this. So you say M4 is year divided by 4, M100 is year divided by 100, M400 is year divided by 400. If M4 is not equal to 0 or M100 equal to 0 and M400 is not equal to 0, then you conclude that it's not a leap year. So you set the days in array, the second value for February to be 28. Otherwise that you conclude that it is a leap year and set the number of days in it to be 29. Now you start calculating. Num days is, start with the days in the 2 months that were there. So day 2, go there, plus the number of days in that month that you're specifying minus day 1. Now you add the days in the intervening month. For that you have a for loop where you say number of days is from whichever month that you were in month 1 plus 1 till the second month. Add that value to the number of days that you had in the leftover months. Now you return the number of days. This is just the program. Our focus is not on this program for this particular lecture. Its focus is on the preconditions which we want to specify as logical predicates. So now this rest of the program basically gets the inputs, then checks the preconditions as formulas. So you remember we had these preconditions, day 1, day 2, month 1 and month 2 must be between 1 and 12, sorry. Then day must be valid day between 1 and 31. Actually, it should be between 1 and 30 for April, 1 and 28 for a non-leap year February, but I'm just generalizing it for the purpose of understanding. Month 1 should come month before month 2. These were all preconditions that were given to us. So I'm just going to write. So if any of these preconditions are violated, we will output a message accordingly. So we'll say if month 1 less than 1 or month 2 is greater than 12, then you say invalid month. Similarly, same thing for month 2. If it's less than 1 or greater than 12, then you say invalid month 2. Then if day is less than 1 and greater than 31, then you say invalid day 1. Similarly for day 2. And as long as month 1 is greater than month 2, you get their inputs. Then you do this invalid year. Call this method calendar whose code we saw here in this slide, this particular part that started and ended here, and return the value. That's what it says. Result is so much. Now let's look at all these preconditions that we coded. A month 1 less than month 1 less than 1, or month 1 greater than 12 for month 2, for day 1, for day 2, and so on, for year 1, for year 2, and so on. So this can be thought of as one large predicate for the entire method that specifies the complete set of preconditions for the calendar program. So the complete set of preconditions, I'm just rewriting it once again here. The range for month 1 between 1 and 12, the range for month 2 between 1 and 12. Month 1 should be number before month 2, the range for day 1, the range for day 2, the range for year. This whole predicate is a formula, as you can see, in conjunctive normal form. There are several clauses, each of which is an individual entity, like month 1 greater or equal to 1, month 1 less than or equal to 12, like that. The whole predicate is a CNF formula. As I told you earlier, these preconditions are not exactly truthful to the method, because, like, for example, if it was April, then you should say number of days is actually 30. Same for September. Then if it is February, then it's 28 or 29. We've not said all that, so we live with the incompleteness, but I hope you get the intuition that the whole set of preconditions can be specified as a predicate. In this case, it happens to be in conjunctive normal form. When it's in conjunctive normal form, we can do the usual ACC criteria along with predicate criteria, clause coverage, and so on. What is the use? The use is basically to check if the method actually satisfies the sequencing constraints or not, if enough exception handling has been done, if you get invalid dates for any of the inputs that are out of range. So predicate coverage will say all clauses need to be true and false. One clause needs to be false for the false case because it's a CNF. Clause coverage says each clause make it true once, make it false once. This requirement cannot just be met with two cases because some clauses are correlated. So here is an example. Month 1 cannot be less than 1 and greater than 12 at the same time. If you see here, no, month 1 cannot be less than 1 and greater than 12 at the same time. So you need to manage that correlation properly and adjust out clause coverage. For ACC criteria, because it's in CNF, we make all the minor clauses true, and for the remaining test, each clause, major clause, is made to take false in turn. So the summary of this example was to help you understand how logical predicates come in as sequencing constraints. Earlier when we saw graphs, we saw how graphs came as sequencing constraints. And most of the logical predicates that come as sequencing constraints either come in CNF or in DNF, in which case I can do predicate and clause coverage the usual way. For ACC, I do this true-false value combinations very easily. And testing these preconditions can also lead to a, here we don't have to bother about reachability, infection, rewriting, and so on. We could take the predicates as it is. The only issue is if the preconditions are given in English, it's our responsibility to write them down as logical expressions, and we should do a correct job as testers. And once we have them and we realize that they are in CNF or DNF, then testing for them becomes a very easy job. So this was one example of how predicates, logical predicates, come in sequencing constraints. In the next lecture, we'll see one more example of how logical predicates come in a different kind of software artifact, namely that of a finite state machine specification of a requirement or a design. I'll stop here. Thank you.